Welcome to Chapter 18, Part 3. Lenses make use of light's refracting property. Converging lenses cause rays to refract toward the optical axis, which is a line through the center of the lens. If this is our converging lens, the optical axis goes right through the center. Parallel light beams converge at the focal point. So parallel light rays are coming in, and then they go through this point on the other side. It doesn't matter where they're coming in from, so long as they're parallel, they will always go through that focal point. That's the definition of that point. The distance from the focal point to the lens is called the focal length, which is symbolized as a lowercase f. This is saying that for a converging lens, light beams that come in parallel all meet at the same point. But also light beams that come in traveling through the focal point emerge parallel. It works in both ways. Example 6 is going to show us how to analyze these problems. Start by drawing the lens and the optical axis. The larger you make it, the more effective this method is. Label your focal points. You're going to want to use a straight edge. Now, draw the object as an arrow. You want it to be about half the size of the lens. The base of the arrow should be on the optical axis. Now we draw 3 rays from the top of the arrow. The first ray will start parallel to the axis. When it hits the center of the lens, it will bend through the far focal point. Extend it out further. The second ray goes through the near focal point and emerges parallel. The third ray goes through the center of the lens. It does not bend. Where all 3 rays meet, you draw the image. This method is useful for determining the orientation and approximate placement of the image. There are 4 words that we'll use when describing an image. We use the word upright to describe an image with the same orientation as the object. An inverted image is flipped. The top picture here shows an inverted image, while the bottom one shows an upright image. A real image is formed when light rays converge on the opposite side of a lens. This is an image that can be viewed on a screen, like a projector. Then we have a virtual image. A virtual image occurs on the same side of the lens as the object. There is no actual light reaching this point, but our brains think there is from tracing the rays back. Using principles of similar triangles, ray tracing, and the blood of a sacrificial goat, we're able to get an expression relating the object distance, image distance, and focal length. This gives us 1 over s plus 1 over s prime is equal to 1 over f. This is an important equation we will be using a lot. We can also use this to define magnification. Magnification, or M, is the height of the image, h prime, divided by the height of the object. This is also proportional to minus s prime over s. If magnification is negative, or the image has a negative height, which would be below the axis, then the image is inverted. A positive magnification is upright. In a diverging lens, light is dispersed. Even so, we can still trace the rays. A ray that comes in parallel to the axis will bend to create a path through the near focal point. There is no actual light there, but the rays appear to follow that path. Rays aimed toward the far focal point emerge parallel. Rays towards the center keep a straight line. They do not bend. For a diverging lens, we can still use the equation of 1 over s plus 1 over s prime equals 1 over f. Except, in this case, f is negative. This means that s prime and f, so the image and the focal point, are on the same side as the object. We also have two types of spherical mirrors, concave and convex. A concave mirror bends in and has an external focal point. A convex mirror bulges out like a ball, and this has an internal focal point. In both cases, parallel rays meet at the focal point. This is located at half the distance of the radius, or we can say that f equals r over 2. In a concave mirror, rays that start out parallel to the axis reflect through the focal point. Rays traveling through the focal point emerge parallel. That can be seen in the second one. A ray passing through the center will reflect to the opposite side of the axis. In this example here, if we trace the rays, we will end up with an image that is real and inverted. We can still use the same equations. In a convex mirror, the focal point is on the inside of the mirror. This is the mirror that's shaped like a ball. Rays that begin parallel will reflect as though they came from the focal point. Rays directed towards the focal point will be reflected parallel to the axis. And any ray directed towards the center of the mirror, or where the axis meets the boundary, will reflect to the opposite side of the axis. The focal point is negative, and so is s prime. This means that for all object locations, the image is virtual and upright. So no matter where the arrow or object is placed on the optical axis, it will always be virtual and upright. A convex mirror will never give a real or inverted image. As a recap, let's go over the sign conventions. In a mirror, the outside is positive, and the inside of a mirror is negative. With lenses, sign is assigned based on the position of the object. Anything on the same side as the object is negative, while the opposite side of the lens as the object is positive. Now, let's look at each quantity. S, or the object position, is always positive. So if you have a negative object position, you should probably just give up and surrender to the void. S prime, the image position, is positive when we have a real image. This is on the opposite side of the lens as an object, or in front of a mirror. A negative image position indicates a virtual image. This would be on the same side of the lens as the object. It would also be behind a mirror. The focal point F is positive for a converging lens. It's also positive for a concave mirror. Focal point is negative for a diverging lens and a convex mirror. Magnification, or M, is positive for an upright image, and it's negative for one that's inverted. We can make use of this with some examples. We will do that in part 4. See you then.